Just 2 more minutes. Hello, everyone. Okay. All right, it's 7 now. I hope. I think a bunch of people are still left. A lot of people are joining in. We just try to introduce ourselves. We will start with the session at after the introduction and what's on today's agenda. A bunch of people are joining in. We'll just give it maybe a minute more because there's a lot of people who have registered for this event. So we are hoping a lot of people don't miss out on the introductions. Just just a second. The session would be about an hour long, or maybe a few more minutes longer than a bit more hour because we have some time constraints as well. It's morning in California, so sure has some time constraints. We must attend to other things as well. We'll keep this session interactive because any questions you have, you can type in the chat. All right. Okay, I'll start. Uh, Hello, everybody. I'm Yash, one of the team members of Propagation. We are here today to give you some insights on the great missions that are going on from Earth, obviously from Earth. But we have a very esteemed guest today, Dr. Sankhabrata Chandra. He has done a bunch of work in this topic. We are here to introduce you to a bunch of things. He is a researcher at NASA Jet Propulsion Laboratory. He has done a PhD in atomic and molecular physics from IISc Bangalore. He has done extreme amount of works in this field. So he is the right person to answer to you of any queries that you might have for this topic. All right. He'll start with the great mission of Europa Clipper mission, where he has been researching for over 2 years, I think. So there's a bunch of information that is about to be thrown at you. I hope you're ready. This session will be recorded, so you'll be able to view it afterwards as well. I hope you have good questions. Yeah, I think you should keep the questions related to this mission itself and some others. A lot of people ask career questions. You can ask them as well, but towards the extreme end. Okay, we'll start with today's session. Uh, we are, first of all, very thankful to our today's guest. He's an extremely gentle and kind human. He has helped us a lot. We have with us our team today. We'll start with the session currently. I'll move the mic to our today's guest. Let's start with the session. Thank you, sir. Here you go.
For your kind words. Can you hear me, right?
Yes, yes, sir. We can hear you.
Let me share the screen. And can you see my windows? I mean,
Yes,
all the slides, right?
yes, 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 yes.
Okay. So thank you all for being here, and good evening all, and good noon and good morning who are joining from UK and USA. And in the next 30 minutes, we will be flying together on a space journey where we'll be seeing the water world in different planetary systems. And those water worlds are very much similar to our own Earth. And in some cases, the amount of water on those systems are much, much higher than the water we have on Earth. But before that, I'll be giving you a short bio and my journey from India to US. And then I'll walk you through the mystery of Europa and how much we know about the habitability of Europa. I'll also show how the how NASA is trying to understand the habitability through Europa Clipper mission, and I'll also give some details about the instruments, what it is on board on the Europa Clipper mission, and how my research work is or the laboratory work is contributing to the Europa Clipper mission. So by training, I am a chemist and I did my Bachelor of Science degree from St. Xavier's College, Kolkata, from 2010 to 2013. And while pursuing my chemistry degree, I was thinking to pursue my work on astrochemistry. However, that time, almost 10 years ago, there was not much options of astrochemistry in India. And with that intention, I moved from Kolkata to Bangalore to pursue my career along the chemical physics and continued my degree on master's and PhD on chemical physics. And during that time, I started working on astrochemistry on an independent project. And on that project, I was trying to understand how the prebiotic molecule forms or how the life forms on Earth. And while doing that, I gained the confidence that how can we try to understand through experimental perspective, how can we generate more complex prebiotic molecules or the biological species in the experimental lab to understand or to gain more confidence on the interstellar dust surfaces. I worked on different labs in US and Europe on astrochemistry before moving to NASA Jet Propulsion Laboratory, where I'm currently work here on the Europa Clipper mission. And I am a postdoc here, mostly working on these things. And my research work at JPL is focused on understanding the future detection of material from two of the Europa Clipper instruments, which I'm going to show in my future, in my later presentation. So those who do not know about the Jet Propulsion Laboratory, which is one of the 10 NASA centers, and this is only federally funded research and development NASA center. And this is based on Pasadena, very close to the Los Angeles city, and Caltech manages this for NASA. Therefore, we are also a part of Caltech community. And JPL is the leading center for exploring the solar system by sending robots and spacecraft. And most of the very detailed information, what we know today about the solar system, that actually come from the Jet Propulsion Laboratory's missions. And already we know very much about the Mars rovers. Those Mars rovers are actually assembled on the Jet Propulsion Laboratory's clean room facility. And very recently, the NASA mission launched, that is a joint mission by NASA and ISRO. The L-band synthetic aperture radar that is installed on the Jet Propulsion Laboratory's clean room facility. And then it moved to the ISRO's center, and then it launched from Sriharikota. At JPL, we asked one of the biggest questions, but not only at JPL. When we are look into the night sky, we also ask the same questions to ourselves. And the question is there any life that exists in the solar system and beyond? And so far, we have only one data, and that is our home, our Earth. And we do not have any data where we have found life so far. So to understand how life forms, there are three ingredients which are necessary to evolve life: water, chemistry, and the energy. And that the time is the most important factor for all of these. All these factors have to be sustained for millions of years, then only system will be habitable. The best example where these three ingredients are present over millions of years is our Earth. And still searching are going on the other planetary bodies. So far, best we know that some of the moons from different planets have water as a liquid form. For example, Callisto, Ganymede, and the Europa. Those are the Jupiter's moon, and those contains significant amount of water. For example, the Callisto contains almost the four times water the Earth we have. Ganymede contains about six times water, and Europa contains about 2.4 times of water compared to our Earth. There are other moons of different other planet also. For example, the Saturn's moon, Titan, and the Enceladus. Titan contains almost 11 times water on its body, and Enceladus contains very tiny amount of water, that is 0.01 times of water. Now, let's see how these small satellites are corresponding to the different planetary systems. So that's why let's take a brief journey about in the solar system. So we have, and also let's try to see how water are there in different other terrestrial bodies. So we have Mercury, Venus, Earth, and Mars. Those are the terrestrial bodies. And we know that we have water on Earth as a liquid form, as a vapor form, and also as a ice form into the polar region. Mercury contains some amount of the water as a ice form into the different craters region. Those are the permanently shadowed region, where the temperature is much less than the water freezing temperature. And Mars contains some amount of the water as a ice form on the polar part. After the asteroid belt, we have the gas giant Jupiter and the Saturn. And the satellites of those Jupiter and the Saturn's moon, and sometime on the Uranus and the Neptune moon, those also contain some measure of the water as the ice form. And also a major amount of the water as a liquid form are also there. And that water is actually sandwiched in between the rocky mantle and also onto the ice surface. Now let's look, since we are mostly focusing on the Europa, let's focus on the Jupiter's moon or the Jupiter's different moon things. So Jupiter has several moons, more than at least 90 moons. However, these 4 moons are really important. Those are Io, Europa, Ganymede, and the Callisto. And these are important to the space science community as well. Io is the most closest moon of the Jupiter, and it has millions of volcanoes. And this is the most volcanic moon for our solar system also. And why it is that? Because Jupiter is so massive. That's why, because of the tidal interaction between the Io and the Jupiter, some of the magma, it generally erupts over time to time. And even from the ground-based telescope from Earth, we can detect those volcanic regions. And it continuously emits charge sources or the charge particle, and those charge particles are in energy region from kilo electron volt to mega electron volt region. And those charge particles generally traps into the Jupiter's magnetic field, and those I'll be showing a little bit later also. Then we have the Europa, and Europa is the most smoothest object. And all these moons are also called the Galilean moons because Galileo discovered these moons in 1610. And from that point, actually, we get to know that our Earth is not the center of the universe. And from this point also, we know that there are four different moons of the Jupiter. So we are coming to the Europa again. So Europa is the most smoothest object, and if you see through the telescope, you will see it will see a very bright one. There are two other moons; those are called the Ganymede and the Callisto. Those are little bit less interested to the space science community compared to the Europa, because those contain some amount of the craters, which I will explain again later. Now, most of the information what we know today about the Io, Europa, Ganymede, or the Callisto, that is because of the very large number of missions which is operated by NASA. The first missions operate, that was Pioneer 10, which went in 1973, and then Pioneer 11 in 1974, and later Voyager 1 and 2 in 1979. These spacecraft captured the images, and by the magnetometer instrument from this spacecraft captures the charge particle distribution around these planetary bodies. But the detailed information what we know today about the Galileo spacecraft, which launched in 1989, and it reached to the Jupiter in 1995, and it spent 2 years orbiting the Jupiter. And by now counting the number of craters, we get to know that what is the age of the moon. However, on the Europa, we have very less number of craters on the Europa surface. And that's why by counting the number of craters, we know that the surface is not much old, and we generally predict as 40 to 90 million years old. And its core is iron and iron sulfur with silicon mantle, and the total surface is covered with water ice. And we have the possible existence of the liquid water, and that is sandwiched between the sandwich between the ice layer and the rocky surface. Just like the in the Antarctica, when we go, when we see the water as ice form, but underneath the ice, we have the water. Just the same thing we have on the Europa. But not only on the Europa, we have the same thing for the different other ocean wall system. For example, the Enceladus or the Callisto or the Ganymede, what I was mentioning before. But the thickness of the water ice that changes from one planetary body to different planetary body. For example, on Europa, we have the thickness of the ice in the range from 10 to 15 kilometer. And after 10 to 15 kilometer, we have the ocean layer, and that ocean layer is almost 100 kilometer thick water layer. And other components are some hydrogen peroxide, some CO2 as a ice form. Those are generally trapped on the ice surface. That we generally know from the Galileo's NIMS data, that is the near infrared mapping spectrometer data. Also, if we zoom into the Europa, we see that there are very scarce. For example, there are very brown color scars are there. And when you zoom to a particular region, and here I'm showing here the 200 kilometer to 250 kilometer region of the Europa surface, we'll see three different color region. One is the very much white color patches, and then we have the pale blue, and then we have some scars with brown color. These white colors are the pure water ice, whereas the pale blue color are the radiated water ice. And where this radiation come from, I explained a little bit before, but I'll also going to give you a much details of the radiated nature of the water ice a little bit later. And the brown color appears because of the non-ice material or the non-water ice components. That could be salt, radiated salt, or could be radiated organics. And if we zoom in again, so currently we are seeing the surface from 200 kilometer to 250 kilometer region. But when we zoom, let's say more than 10 times, we'll see this kind of features. And this region is from 14 kilometer to 70 kilometer resolution. And on the right side, we see the resolution about 20 kilometer by 20 kilometer. So in the left side, we see a very much double ridges. So these are called the double ridge on the Europa, and these are very, very famous actually. And this is very much comparable. Already we see these kind of features on Greenland ice. And these kind of features actually appear when there is a tectonic activity between two ice layers, and there is a break of these two ice layers. Some of the water as a liquid form just upwelled from the liquid portion to the solid portion, and that's why these double ridges form. But on the left side, when we are looking at the double ridges, we are seeing that in some part, at least in two regions, which is shown here in these two regions, these double ridges are actually discontinued by another double ridges. And that's give more confidence about Europa, that Europa surface is still continuously changing. And these changes occurs because of the tidal motion, So since Jupiter is so massive in nature, and already we know that we have water on the Europa. So because of the tidal forces, those ice cracks and some of the waters comes out as an upwell, and we'll see some of the geysers sometime and some of the double ridges formation. And this is, and when the Galileo spacecraft flew on the Europa system, it detected a very strange signal from its magnetometer. And that actually explained only if we think that there is a faulty ocean layer underneath of the icy surface. So I was talking about the Europa's radiation condition because we see some pale blue color or the dark brown spots on the Europa. And that appears because of the radiation condition on the Europa. And since Jupiter is so massive, it has huge magnetic field. And already I talked about the defined moons of the Jupiter, that is the Io and other moon such as Ganymede and the Callisto. But Io is the most important thing for this thing. Because of the very much huge magnetic field and the huge gravitational pull, it emits huge amount of magma into the space or huge amount of the charged particle into the space. And those charged particles are trapped inside the Jupiter's huge magnetic field. And those charged particles co-rotates with Europa and continuously bombard on the Europa surface. And now think of, just like our moon, we can see only one side of our moon. We cannot see the farthest side of our moon. Similar, which means that our moon is phase locked with Earth. Same thing happens for Europa. Europa is also phase locked with the Jupiter. So one side of the Europa is continuously phased on the Jupiter side. Therefore, when the charged particles are bombarding on the Europa surface, it is continuously bombarding only a particular part of the Europa. And that's why we see a clear color distinction of the Europa surface. So one side of the Europa is totally white in color, whereas the other side of the Europa, it is totally dark in color. And this appears because of the high radiation dose. And how much is the radiation? For example, when we take the chest X-ray, we know that we got some amount of the radiation. And on the Europa is getting almost million times of the chest X-ray. So you can imagine how much is the radiation dose every second Europa is getting. So that's why we need to be very careful when some spacecraft is flying by the Europa, because it is also interacting with the radiation system. So let's look into the much details also about the ocean seafloor. So already we talked that we have the 100 kilometer thick, around 100 kilometer thick ocean layer underneath of the icy surface. And this ocean layer is continuously interacting with the rocky seafloor. And because of the interaction and also because of the hydrothermal vents, it is continuously changing its composition inside the Europa's ocean. So not only we have different kinds of salt, for example, we have table salt, what we generally take in food, and we are predicting that the composition of the Europa's ocean is very much similar to our own Earth, because our Earth ocean is also interacting with the ocean seafloor, and that actually helps to create the energy, and that actually also helps to synthesize prebiotic molecules, or it actually helps to form life. And already we talked about the tidal interaction, and because of the tidal interaction and the tectonic activity, the two ice layers when just collide, it breaks, and the liquid water can just erupt as a geyser or as a plume to the space. And Europa Clipper we are thinking that Europa Clipper can detect those plume or the geyser when some water is actually erupting. And this is not the first time we are aiming these things, but previously NASA's Cassini mission that flew for the Saturn's moon Enceladus, that actually captures the direct image of the plume when it is coming from the Enceladus ocean. And if we detect some of the materials which are coming from the ocean, then we can understand what are the materials, or what are the microorganisms, or what are, if there is any life, or if any life containing molecules are there underneath of the ocean or not. And how we are going to do that? So when some of the water is coming through as a plume, so and at that time Europa Clipper will be flying by, and because of that it can detect some of the materials. And how we are going to detect those things? By using different number of instruments. So Europa Clipper has almost 10 scientific instruments. Those are categorized as remote sensing instrument, chemical analysis instrument, radar and gravity, plasma and magnetic field instrument. Obviously, this plasma and magnetic field, plasma magnetic field, and the chemical analysis instrument are the in situ instrument, and those measures the particles in situ while flying by the Europa. But also some of the remote sensing instruments, those are very, very important for the future missions also and for the scientific return. For example, the Europa imaging systems, it captures the image in between the 350 nanometer to 1050 nanometer. And it will give the information how the Europa look like in much greater detail, sometime around 20 to 25 kilometer ranges. Thermal imaging systems, from the thermal imaging system, we get to know that what is the temperature of the Europa, what is the nighttime temperature, what is the daytime temperature, what is the temperature on the equator part, or what is the temperature on the polar part. Europa ultraviolet spectrograph will give the information about the hot spot. Some part, let's say, having very thin layer of ice, and if let's say our ocean layer is very much close to the exosphere, then those points will be very much interested for the future lander mission. Let's say if we want to land on the Europa surface, and if we want to drill, those points are really, really important for future study. And the mapping imaging spectrometer will give the clue what is the surface composition, what we have on the surface on the Europa. Plasma magnetic field measurement will give the information about the charged particle sources on the Europa, and that will help for future lander mission and how we can protect our spacecraft in a better way. Radar and gravity data will give the information about the how much thick layer of ice we have on the Europa surface. And the chemical analysis instrument, those are the two of the mass spectrometer. And here my contribution is, or the laboratory data plays a role to generate some of the data for the mass spectrometer for the chemical analysis instrument. And we have two of the mass spectrometer. Those are called the mass spectrometer for planetary expression, or mass specs, or the surface dust analyzer called SUDA. But why we have two mass spectrometer? And in this two mass spectrometer, that has different roles actually. The surface, it's more like surface dust analyzer or the SUDA will actually smell the material, whereas mass spectrometer or the mass specs can generally taste the material with much greater details, and both having the mass range of 500 AMU. So with all this instrument, Europa Clipper spacecraft was assembled at the Jet Propulsion Laboratory, and it transferred to the Kennedy Space Center, where it is flew to the Europa on October 2024. And now it is into the space, and it is making its journey to the Europa. So it will take two gravity assist from the Mars and from the Earth. So already it used one gravity assist from the Mars on last March, and it is now coming towards Earth, and it will use another gravity assist on December 2026, and it will go towards the Jupiter, and it will reach to the Jupiter in 2030. and then it will make almost 50 flyby. I think it is 49 flyby on Europa, and it will capture different scientific information and it will deliver to the Earth. Now let's look into the details or how our contribution is for the Europa Clipper missions, or the how our contribution from the laboratory work side. So as we mentioned before, that our laboratory data actually helps to understand the some of the surface convection, or when the Europa Clipper will be flying by, how we can interpret those data. So this data will define the requirement of the sample collection, position, and the analysis. And also, this data will significantly impact the interpretation of the data collected by the mass spectrometer and the SUDA instrument. And how we are going to do these things? So we need to create the similar environment just like Europa. So we know that what is the surface composition of the Europa, what is the temperature of the Europa, or what is the vacuum atmospheric pressure on the Europa. From that point, we generally simulate the environment just like Europa. And already we talked about the energetic charge particle bombardment on the Europa surface. So when this charge particle are bombarding on the Europa surface, it generates small tiny particles into the exosphere. And our mass spectrometer, that is called the mass specs, which is shown here, that is actually installed on the Europa Clipper spacecraft. So that captures some of the molecules or some of the particles which are generated by the charged particle bombardments. And we are predicting that these mass specs can actually detect those of the tiny particles. And when it will detect those of the tiny particle, we will have a significant amount of the data. And if we do not have any calibrated data before from the experiment from the lab side, we will be totally clueless after seeing those data. So that's why we need to generate those data before we are really getting the real data. So how we do that? We generally mix the Europa analog samples on a vacuum systems, and we use high radiation dose by using electron gun or the ion gun, which generally creates energy from kilo electron volt to mega electron volt region. And we use different kind of water ice and also sometimes organic ice. Let's say some of the materials erupt from the ocean to the surface, and those are let's say some organics, and those are let's say continuously changing by the charged particle sources. Then how can we understand how those organics can behave in the charged particle regions or charged particle interaction? So we are mimicking exactly the same environment, and also we are trying to understand how the equator region of the Europa, or the day side or the night side of the Europa, can have different kind of interaction. And we have already found that from our experiment, the day side or the equator region of the Europa can emits huge amount of particles into the exosphere compared to the night time and compared to the polar region. So we are suggesting that when the Europa Clipper will be flying by on the Europa, it should actually turn on its instrument on the day side equator region. Then only it can detect more and more number of particles. And if we collect more and more number of particles, we have better intensity, we have better understanding on the we have better understanding of Europa. Also, the another instrument I'm currently working on, that is called the SUDA, and we are that is the surface dust analyzer, and we are actually replicating the geyser of the on the Europa. So we already talked about the tectonic activity or the tidal interaction because of the Jupiter massive magnetic field, Jupiter massive gravitational pull. So some of the liquid water will erupt when there is a crack inside in the ice junction, and those water just erupt as a geyser or a plume. And since there is not much atmosphere on Europa, whenever this water erupts from the liquid state to the vacuum state, it immediately forms very, very tiny ice particles having sizes in the range from nanometer to about micron size particles, ice particles. And let's say if we have some of the bacteria, or let's say some of the viruses which are, let's say, on the ocean, and when these water are actually erupting on the Europa's exosphere, it actually captures those of the bacteria or viruses into the space. And when the Europa Clipper will be flying by, then it will also capture those tiny ice droplets. We are trying to find out, can it really detect those microorganisms or the bacteria which is actually inside the ice droplets or not? And we are doing these things by using a liquid microjet technique. And in the liquid microjet technique, what we generally do, we use the similar kind of ocean composition, just what we have on Earth, salty ocean composition, and we use that liquid microjet, and we disperse that liquid by using IR laser, and makes the ice tiny droplets into the micron size. And sometimes we use some of the complex microorganism. Those can sustain even if we do not have any oxygen. And we are trying to find out if those bacteria or the microorganisms are actually inside the tiny ice droplets. Can our instrument detect those droplets? Can it detect those microorganisms or not? And if it is detected, then we are very much confident that our SUDA can also detect those of the complex materials or the complex species, if, let's say, if it is there on the Europa. But still, we do not know what it is there. Only we know that there are some salt water or some silica nanoparticles are there. So we are trying to understand better by these Europa Clipper missions. So the take-home message is that the Europa is an icy world, and the Clipper mission will going to understand the habitability of this moon. And Europa Clipper mission is not a life search mission. It is the mission to understand the habitability of the Europa. And our lab work will help to understand the sample collection region, and will help to interpret the data for when it will be collecting in 2030 or 2031. And currently we are generating more and more data to understand how the Europa Clipper will behave at later time, so that when it will be really collecting the data, we are not be confused by looking at the data. There are also other missions to the other ocean world systems which are currently NASA's planned. For example, the Dragonfly mission, which will be exploring the another ocean world called the Titan, which is a Saturn moon. And this will be a car-size spacecraft. And Titan has actually little bit thick atmosphere. Therefore, Dragonfly actually can fly just like a drone. It will just fly from one particular position on the Titan to another particular position on the Titan. And what is interesting on the Titan, this is the only planetary moon we have where we have the liquid lake or the liquid river. But those are not water as a liquid form. Those are actually hydrocarbon liquids. And when we have such kind of organics, we are thinking that that will be the best place to explore if there is any life containing molecules are there or not. So Dragonfly will be exploring some of the very details of the Titan. So none of this work will be possible if we do not have this amazing team. So our different scientists from different parts of the institute or in the US are contributing for these things. And for the laboratory work, Murthy Guripati from the Jet Propulsion Laboratory, Brianna Henderson from the again from the Jet Propulsion Laboratory, Morgan Cable again from the JPL are my advisor, who are actually helping us to understand how we can get more data and how we can better understand the Europa system. Paulo Simo and Marcel Seaton are also helping for these things, and the whole work is supported by the NASA's Habitable World Exobiology and the PSI program. And I'm happy to answer any of this question, and thank you all for the listening. And
All
also,
right.
if you want to contact with me in person, or, I mean, through my email ID, you can check my JPL email ID or my personal email ID. You can ask question. I'll be happy to answer. I'll be happy to answer all those questions.
Nice, nice. It was great. It was absolutely awesome. Now it's time for an interactive thing. Will people who have the questions, you can ask the questions directly to sir. You can raise your hands firstly, then you can turn on your mic and your camera if you're not in a very upstanding position. You can turn on your mic and ask the question right away. All right. We'll take the questions right now. So people who have doubts, people have asked a bunch of questions in the chat, but firstly we'll take the voice questions. So if you have any doubt, please raise your hands. We'll take the questions right now. President India, yep.
Okay.
Okay. A bunch of people. I think there was somebody called Saptaparna. I think
Mhm.
she had questions. Okay, I think she has not raised her hand. We'll take her questions in a few minutes. We'll start
Mhm.
with the Jagrati Singh. Jagrati, you can open your mic and start with the questions. Wait a second.
Uh,
Jagrati.
Hello, sir. Oh, sorry.
Yep.
Hello, sir. So my name
Yep.
is Jagriti. I'm is first year student. So I want to know, like, as you are finding the life, right, in solar system. So what's the definition of life according to you? Because while understanding first year biology, I find
Mhm.
like I feel that as we understand the evolution, they are explaining that something chemical reaction happened initially because of that
Mhm.
DNA and like RNA specifically form and the life evolve, right? But if
Mhm.
certain different type of condition was there, different type of thing was happened which caused the formation of life. So what will
Mhm.
happen? It might be possible our senses, like how it works and understanding of the world was completely different, which was not as same as we are understanding right now because we are explaining the life according to our limited senses and all. So it
Yep.
might be possible there is life in another, in our solar system even might be, but we won't able to understand that, yeah, that is the living thing. So how would we conquer this problem?
Okay, so the definition of life is actually changes from one community to another community. So basically, and also it is changes especially into the planetary science region. For example, astrophysics thinks of uh, uh, detection of life means detection of some of the uh, complex things. For example, let's say methane or some, let's say, dimethyl sulfide. So if you detect those gases in some of the solar system, or let's say outside of the solar system in the exoplanet, then they think that they are detecting life, or let's say life containing molecules, because those are the gases can only be possible if we have some those are the actual generate if we have possible existence of life, something like that. But when it comes to the chemistry side, methane dimethyl sulfide are the very small molecules. They think that when we have very much complex molecules, then we, for example, let's say DNA, RNA, or let's say amino acid, if those are molecules are there, then we have possible existence of life. But now when we come to the biologist, then we think that we should have the life as a proper form. Let's say some microorganism if we detect, or let's say some on some planetary bodies. For example, currently Mars, on Mars, Mars rover, it is detecting some of the complex fatty acids. Those are very much close to the life-containing molecules. So it changes from one community to another community. And so far, we exactly do not know what is the how we can make the definition of the biosignature or the life. And there are still some publications are still going on into the into a journal called astrobiology. So if you just search the signature detection of the biosignature, or let's say the definition of the biosignature, there are lots of materials on the astrobiology journal, and you will see that those definition changes from one community to another community. And that is true because you cannot actually detect through remote sensing observation any life containing molecule or any complex molecule if it is there in the exoplanet. And that's why it changes from over time to time, and it will evolve over time to time also.
Okay, sir, it might be possible we are doing somewhere wrong way for finding the life because, like, according to me, like I used to thought little bit philosophically because I used to
Mhm.
thought that it might be possible the words which we are using isn't exist. Like the definition, like life definition. We used to say that life having some definition, but definition is just a word which was for our understanding. Okay, this is what we call that. Okay, we can able to understand, but might be possible something is beyond our understanding. Like there is a life, but we wouldn't able to identify. We are just with the limitation of our senses. Uh, like if there is a lot of thought, like I do have a lot of thought, but I wouldn't able to
Yeah.
share.
Yeah,
But
yeah, that is very true. For example, that's why the next mission is the Dragonfly, where it will be exploring the Titan moon. And on the Titan moon, we do not have the water as a liquid form, but we have the hydrocarbon as a liquid form. There we have hydrocarbon rain also, and hydrocarbon lake also. And if we, let's say, find some kind of life on those lakes, and those life will be totally different from ours, where we cannot sustain into those Titan kind of environment. But if we can find find life on the Titan, those life will be totally different from Earth, and those bodies will not sustain on Earth environment. So we are still evolving. We are still trying to understand how life will be in other different planetary bodies. But since we know our Earth system very well, we know that how the life could be if we have water. So most of the time when we found water in some of the planetary bodies, we immediately give our 100% attention to that planetary bodies, because we already know that life is possible if we have liquid water, if we have correct temperature, we have correct energy into the water system, and if it is sustains for, let's say, millions of years. So it is the idea is still evolving actually.
okay, sir, last question. Sir, like I want to develop mathematics in the biology. Like it's my dream
Mhm.
to find what exactly life is, what exactly reality is. Because according to me, reality is somewhere. Like I'm not telling that yeah, this is wall and this is not a wall. We're just assuming. No, not like that. But somewhere reality is limited, like we won't able to see think everything. So I want
Mhm.
to prove mathematically equation that how our senses work and like what's the actual definition of life. So would you just tell me, like it's just a starting of my journey. So how would I proceed? Because right now today I am just like reading the research paper of Big Bang, like the first
Mhm.
research paper and after so on. So how would I proceed? And my research journey is just my first year.
So from the mathematics side, you were saying?
Yeah.
Oh, yeah. So, yeah, there are actually different mathematical model that can actually help to understand the exoplanetary light detection things, or detect the exoplanet basically. So there are a few research groups I think we have, where they used different chemical model or different mathematical model to generate the codes, and they use actually to detect the exoplanet, something like that. So there are various possibilities, and also into the astrophysics region there are a lot of options from the mathematics side. So your approach will be more towards the pure astrophysics, mathematical in astrophysics, or mathematics in exoplanet detection. Those will be very much important, I think, if you want to pursue your career along that line.
Okay, so like, is there any person like so that I can reach or understand about their opinion and all like
I need to look into this thing. You can separately send a email to me, and then I will look into these things. And if something is coming to my mind, then I will send some information.
okay, thank you so much,
So
sir.
far, yeah, so far kindly, uh, it's not coming to my mind. Yeah.
Okay, thank you.
All right, Jagrati, thank you for your questions. Next, we'll take Savir's question. I think he has
Mm-hmm.
been one of the people who have been asking the questions. Please go ahead, Savir.
Good evening.
Yeah.
So my question is related to the life only. So as we know, there is a news that we just found the micro life in Mars and
Mm-hmm.
everything, the first source of the life. So my question is, why don't we just explore the poles of the Mars? Because the overall they are the frozen water, and I think we can find the Martians here. They're micro and
Mm-hmm.
like.
Yeah. So on the Mars, we have detected some of the materials which are the direct evidence of the life, but still we do not have found any life. And always we try to find various possibility. For example, on the Mars, we know that there are frozen ice, but we still do not have any idea about the is there any liquid system or not. Because liquid, when we have some liquids, either it could be water or it could be some hydrocarbon as a liquid form, liquid actually helps to involve life. And whenever we found liquid, we think that the liquid can be a source of life. For example, underneath of our ocean, where we do not have the sun's radiation, or let's say the sun's light cannot reach, let's say 50 kilometer deep of the ocean, and there still we found near the hydrothermal vent region, we still found life. And that's why people are so much interested about the Europa or some ocean wall systems, because even if you do not have sun, or even if you do not have any sunlight, still in that region you can find some of the microorganisms. And that actually give the interest to the interest to the scientific community, that okay, even if you do not have sun, you can still find some life. And that's why not only Mars, people are exploring different ocean world region, because they have found liquid, they have found the two other ingredients, that's the energy and the right chemicals, or the right chemical ingredients. For example, the phosphorus, the sulfur, those are the materials are very much popular in nature on those systems. That's why not only Mars, but also there are different planetary bodies which are actually useful to look at to find life.
which means that Mars was once a habitable planet,
Mhm,
but only its only size made it an abandoned.
mhm.
My question is only. Thank you, sir.
Yeah, I think we have to give one instruction to you. That is one question per person since we have a time constraint and there are a lot of questions that people want to ask. So we'll keep it one per person. Next person we can take is Sri Lakshmi. You can go ahead and ask your questions there.
Yeah, hello, can you hear me?
Yeah,
Yes,
yeah.
yes.
Yeah, hi. Good evening. So, thank you for the session. It was really informative. So, I am an astronomy educator here working out of Chennai, India.
Mhm,
So, I would like to understand what are the opportunities that I can give my students in terms of exploring the planetary sciences. Like they're already doing a couple of citizen science projects, but
mhm,
like in terms of getting their hands dirty, working with some real data
mhm.
or any other suggestions that you can give, sir?
Mm, I think there are various options from the ISRO's outreach activity. I think I know there are few options are there from the Space Application Center from the Ahmedabad ISRO Center. They do some kind of research activities. So, and also I think there are many internship are possible right now. So engaging through the internship through ISRO's program or through I think engaging into the NASA's internship or the European Space Agency internship that requires, I think, citizenship. I think, or sometimes if some students are actually taking their courses into the US university, that then only it is possible. But I think for the ISRO's internship, it will be very much helpful for advance their career. Um, so I think that having an internship um, will help to understand how to handle the real data. So I think internship is one of the good option, I think.
No, okay, okay. Thank you very much. I think that's helpful.
Yeah.
Thank you, Sri Lakshmi. We'll take Saparna De's next question. Saparna, you can go ahead. Will we have her here? Okay. I think not. There might be some lag. So we'll take Ashutosh's next question. Ashutosh, you can
Oh,
go ahead.
sorry.
Good evening, sir.
Yeah.
Good evening, sir.
Yeah. Good evening. And
Sir,
just.
I am a MSc Applied Geology student at NIT Rourkela, and
Mhm,
I want to ask you a question about pursuing a PhD in planetary geoscience. So,
mhm.
how can I get into the research projects that is interested in planetary geoscience? Studying the structural geology of the planets.
Mhm. I think there are multiple options in currently some of the IITs are actually opening separate space science department. For example, IIT Kanpur, IIT Roorkee, they recently opened. NISA Bhubaneswar has separate space science department, and they have also the faculty from the geology side. So if you contact with them and try to understand how you can contribute to this part to understand, let's say, moon or our own moon, or let's say how you can contribute Mars or different other planetary bodies from your side, and how can you grow your career, or if you can do after your studies, how can you do some project with them that can actually help, I think. So try to look at some of the department, or let's say some of the ISRO centers, the things I was telling, that some of the internship may be helpful in some of the ISRO centers where you can actually work on the real data, and also on, yeah, there are multiple options. I think you need to look into those things.
Okay, thank you, sir.
Nice, nice. I think Saparna ma'am had some problem with the mic. Is she able to open the mic now?
Yes, can you hear me, sir?
Yeah, yeah,
Yeah.
I can hear you.
Okay. Actually, sir, I have many questions, but as it is the constraint that I can only ask like one or two questions. So
Mhm.
my first question will be regarding that whatever data we are having till now, what
Mhm.
are or the process or how we can make mathematical and statistical modeling for the particular Europa satellite. Like we have mathematical and statistical models for
Mhm.
Earth, like for climates or for weathers and separate things,
Mhm. Mhm.
atmospheric or mass like mass movements like ice
Mhm.
depositions and meltings.
Mhm.
So what kind of like how to make similar models for Europe, or is there anything exist? Can you tell me that?
There are definitely there are various options are there. For example, how the I was talking about the charge particle things, right? How the charge particle distributions are, or the how the charge particles are interacting, or the how yeah, mostly I found that the how the magnetometer, especially how magnetometer works, those comes, or the radar part is actually working. Those comes with that mathematical modeling or the statistical data analysis part. I think working along that line may be helpful. That I believe.
Okay, sir. Means
Uh,
we will gather more data when the like Clipper mission will reach there. I
yeah,
guess we can build
yeah,
better
but
models.
also but also I think there is options actually. I remember now. So when the Cassini missions flew in 1990, in 2001, I think. So it captures some of the data in captures some of the data for its charge particle detector, and it just a huge number of mass spectrometer data. Okay, almost millions spectra. So currently one project is currently going on, and we are trying to understand how we can, um, because we have millions of spectra, okay, and we cannot look each spectra at a time. So you need some kind of machine learning things, or some kind of AI things to do on behalf of you, because you have millions of spectra. So one project is currently going on to understand how, when we have millions of spectra, how can we how computer can detects any peak, any sudden peak we see, or any sudden mass we see, that can be interested to the community. So yeah, there are options actually. Yeah, there are options.
So those data are available for like us
No,
to.
I don't think so. But there are some journal which really publish those data. But I think those data are not really available to the community. That's my belief. I think, especially not to the other other foreign national, I think.
Sir, like the same way, we can also build like when the Clipper mission will reach there, will be
Yeah,
able to build the gravitational field modeling, that
yeah, yeah,
how
yeah.
the mass is distributed or how the mass movement
Yeah,
happens there,
that is
right?
that is already some of the research groups are doing. For example, um, uh, at uh, at UCLA, University of California, Los Angeles, Krishnan Khurana, or and his research group are already doing these things. How the gravitational pulls or the magnetic fields are distributed over the Jupiter systems. Those things already they are doing for last 20 to 30 years actually. Yeah,
Okay, so means in that way, we can also do
yeah,
the same, the way we can use the GRACE data and we
yeah,
can
yeah,
detect the things of gravitational anomaly in Earth,
yeah,
right?
yeah, yeah, yeah.
Okay, sir. And the last one is a very small question. Is like, is there any way to like get connected with you for the research collaboration or work with you? Like that is my personal question.
So I mean, we cannot immediately collaborate, but in future obviously yes. You can talk to, I mean, we can have a conversation sometime later, and then we can find possibilities. That's will be one of the options, and we need to find out the options actually.
Okay, thank you so much, sir.
Yeah,
Thank you.
problem. Thank you.
Thank you, ma'am. Thank you.
Find life or life containing molecule on Europa, on let's say Enceladus or Titan, or in those systems, then already we know that in our solar system we have this kind of water world in a large quantity, almost more than 10 to 12 ocean world already we have, which means that in some of the another solar system which is outside our solar system or in other galaxies already have millions of water worlds or the ocean worlds. So then life can be evolved in any place if we have these, if we have the correct ingredients. And that's why we are trying to explore only a particular part, the Europa. And if we try understand that, okay, if life can be found on Europa, then it can be possible everywhere in any of the exoplanet or in any of the water world systems. Though we cannot go there because those are very, very far from our Earth, and just by in a human life we cannot go there, but still we will be knowing that we can found life on those systems. So those are the bigger picture from the Europa Clipper missions we are expecting. If we found that, okay, Europa is habitable, or let's say future Europa lander mission can detect some of the lives, then we can better understand about the life outside our solar systems in different exoplanet, and our understanding will be much, much better.
Okay, thank you, sir. There is another question that I have to ask, which is I'm planning to do a PhD. Like
Mhm.
it's my aim to do a PhD in cosmology. So, is there any advice that you have for me? Currently, I'm exploring and doing some self projects and simulations in it.
What is your background?
I'm pursuing physics honors.
Okay, physics honor. So there are various options from your side. So you need to then choose, I mean, what kind of research you want to do through the astrophysics side, or the planetary geology, or let's say exoplanet detection. There are multiple options for you. So you need to find your own interest, and if you find your own interest, then contact to any of the faculty members in various parts of the world, and contact with them and try to do some project before doing the PhD, because that project actually help to give you a clear idea what you will be spending for next 5 years or next of your life. So having the project for, let's say, few months after your masters, or let's say during your masters, if we do, I think that may help some I mean, that may help to decide what you will be working on in your PhD.
Okay, thank you so much, sir.
Yeah, no problem.
If you have any career questions, you can also mail us, all right, so that it's not too cluttered. We'll take Wabab's question now. So, Wabab, you can now speak. He has been waiting for a long time, so let's do it. And for people who are texting in the chat, please don't get impatient. We'll take your questions where there's a bit of a time limit, so one question at a time. Let's do Wabab's question for now.
Mhm.
Wabab, you can go ahead.
Okay, sir. Very good evening, sir.
Mhm.
I am Vaibhav from, I'm Vaibhav doing BTech in aerospace third year.
Mhm.
Sir, is there any opportunity for me to work with NASA?
Uh, I mean, directly, it is, I mean, you need to continuously check the opportunities. Is there any opening for the foreign nationals? You need to continuously apply, you need to make contact, and you need to also, when, let's say there is some conference going on, if let's say some of the NASA scientists are visiting those conferences, try to interact with them, and also, I mean, don't think that you need to work at NASA, but also think that you need to work on a particular field. And let's say while working on that field, someday you will get the opportunity and you will be working. So try to aim for that particular field which will be working. That will be the goal. And then when you will be working, if you find some opportunity, you can join as a scientist or as an engineer. That will be I mean, that way you can proceed.
Uh, I mean, I had done some citizen scientist projects like just a few months
Yeah,
back. I have
yeah.
started a collaboration. Will it be any useful?
Yeah, definitely. Anything space relevant thing will be used. Nothing will be useless. So every time, whenever you are contributing to the space science, you are gaining some amount of the confidence, some amount of the knowledge from this science, and then you need to continuously gather knowledge. And then when you will find the correct opportunity, then you can just join there. So every time, just I mean, gather some knowledge and do some I mean, whatever work, if you find that it will be useful for your future career, then just do it, I should say.
Okay, sir. Thank you, sir.
Yeah, problem.
All right, Vaibhav, we can take Vandit's question now. Vandit, you can go ahead.
Hello, sir. I'm a
Sir,
freshman from
hello.
Gurgaon. I'm pursuing my bachelor's in engineering. So I do share my specific interest in astrophysics as well. So
Mhm.
I I have a question from aerospace regarding kind of. So my question is, how do the mission's multiple flybys balance the data collection with minimizing the radiation exposure from the moon?
Oh, okay. Yeah, that things I actually skipped. So Europa has a huge magnetic field, so that's why the Europa Clipper will not actually spend much time on the Europa. It will just fly by, and then it will mostly make it will, most of the time, it will be not on the Europa region, but it will be traveling along the Jupiter's region, and then it will make another flyby. So total 49 flyby it will make. So it will spend minimum time on the Europa, and when it will be flying by on the Europa, it will start all 10 of its scientific instruments simultaneously, and it will collect the data. And while passing through the Europa, when it will be traveling through the Jupiter, at that time it will be transferring the data towards Earth.
Okay. So as I was studying the mission itself, in the meantime,
Mhm.
I have one more related question to the same question I asked before. I was thinking that by a highly elliptical orbit is chosen for Europa mission instead of a closer circular orbit around the moon.
Yep. That is because of the high radiation. That's what I was
Okay.
saying, that because of the very high radiation, then the sustainability of the Europa's spacecraft will be low if it will make a circular loop on the Europa, because it has a huge magnetic field, huge amount of the high radiation, starting from kiloelectron volt to mega electron volt, and if it will continuously bombard on the spacecraft, it will just destroy. So that's why it will give a very minimum time on the Europa and a elliptical orbit.
Okay. All right, sir. Thank you very much.
Yeah. Mhm. Yeah, you can ask through my LinkedIn. That will be, you can ask through my LinkedIn. That will be best. And if I am not replying you immediately, but definitely I'll going to reply you in a few days.
Yeah, Resistance has something. You can ask the question next. Resistance, please
Yes,
do.
hello.
Yeah.
Thank you for the session, and I am a ardent admirer of NASA. I have two questions for that
Mhm.
Europa Clipper mission. What is the expected resolution of the ice penetrating radar designed when mapping Europa's surface structure?
Mhm. So so radar is currently help to understand the ice penetration depth, and in some cases it is we are expecting that it is 10 kilometer to, could be possible 100-kilometer thick ice also. And the resolution, I need to check what is the correct resolution for the for that particular scientific instrument. And I am not an expert of the radar, and the current radar instrument can detect up to 100, up to I think 100-kilometer thick ice. That's my current understanding, but I need to also look into these things, that how much thick layer, maximum how much thick layer of ice it can detect, and what is its resolution for the other side.
Okay. And another question is there any chance that we send a human for a Europa mission in nearby future? How will they survive for 6 years in space?
Yeah, so there is currently no plan to send human to on the Europa, but future lander mission is planning. One planning is going on where we are planning to send the Europa lander where it will drill the ice and send the robots to the underneath of the ocean, and it can explore some part of the ocean. So they are kindly testing on the Antarctica where we have the thick layer of ice, and they are drilling the ice layer and then exploring the underneath of the ice, how it can explore just by using the robots. So there is one mission concept phase is going on for the Europa lander side.
Thank you. Thank you.
All right. All right. Is Mridul there? You can quickly ask a single question. We'll do one question.
Yes,
Only. Like,
namaste,
Mridul,
sir. Maybe it's a bit naive, but my question is that how can we say that a planet or a celestial body has water in it? Like, do we send rovers to each of those celestial bodies and say that we receive back data, or is there any other way? And thank you for the team and chief guest for this event. Looking for future events.
For other bodies means the other
Asteroid.
moons, right? Other moons
Yes,
you are
that's
saying?
right.
Yeah,
Moons.
yeah,
Yes.
those, yeah. So those are actually data collected from the different other spacecraft. For example, the Galileo spacecraft actually data from not only on the Europa but also for the Callisto, Ganymede, for those systems. And when it measures the magnetometer from the magnetometer data, we get to know that there is a strange magnetic field for those systems also. And from there, we understand that there are some amount of the water as a liquid form underneath of the ice. So same thing happened for the Enceladus, but Enceladus, it is very much good data we have from the Cassini missions, because it already captures the image that water is actually coming as a jet from the underneath of the ocean. So we have the direct data from the Cassini mission. That is from the Saturn's moon, and also there are a few other for the Uranus and Neptune's moon. I think the New Horizon missions actually captures those data. So there are real data, they are from the magnetometer mostly, which is actually giving the information if we have any ocean underneath of the ice or not.
So if it's visible, it can be seen from the satellite images, and if it's not, then we use magnetometer and other devices.
It is not the satellite image, but this is actually very much important about the if we have the geyser or the plume or not. So let's say the Enceladus is constantly erupting the water from this ocean on its south pole, and because of that, it actually capture image through its Cassini mission. However, for the Europa, there is only one image captured by the Hubble Space Telescope. However, the JWST cannot capture any of the, so far it did not capture any of the plume or any of the geyser on the Europa. So still we do not know. Maybe Europa Clipper can detect any of the geyser that will be, we'll be seeing in next 5 to 6 years.
Okay, sir. So I have another question regarding career, which I will email you or in LinkedIn.
Yeah,
Thank you.
sure. Yep.
Thank you, sir.
Mridul, thank you, Mridul. We'll take maybe two more questions. That's it. All right. We'll take Pratish's question. Pratish, you can go ahead right away. So we can make this quick.
Good evening, sir. Am I audible?
Yeah.
Yes.
Sir, my first question is, there is an asteroid belt between the Mars and the Jupiter,
Mhm.
and how do we escape those belts? Because there are lots of asteroids which collide with our satellites and many other things, and how do we escape them?
I have actually very much little bit. So when I think they know that if there is any object which is coming closer, though, so they can change slightly. I think their navigation. So that's my current understanding. I am also trying to understand how the navigation engineer operates the spacecraft while going towards the Jupiter system, Saturn system, or Uranus Neptune systems. Yeah, those I think it is the navigation engineer. I think they use the radar's data most of the. That's my understanding. But you can also take a Google search, or talk to some navigation engineer if you have option. They can give you the best answer, I think.
Okay, sir. Sir, my another question is, you have mentioned that most of the moons doesn't rotate on their axis. Why
Yeah.
does it happen? Like Earth rotates on
Um,
its axis,
I,
but another moon doesn't.
I think this is based on the gravitational pull. So let's say if one planetary body is so tiny compared to the mother planet, then the and if that moon is so small, then then it will be phase locked because it cannot rotate. It doesn't have its own gravity. It doesn't have its own gravity much, so it cannot rotate by its own. That's my understanding.
Okay,
That could
sir.
be one
Thank you
of the
so much.
things because Jupiter is so massive and Europa is so tiny, and that's why it probably phase locked.
Okay, sir. Thank you, sir. And one more thing, last, you have mentioned one thing that craters on the planet, exoplanets, tells us about the age. Then how does that decided that that amount of craters? I try to
Oh,
ask,
so
how does
yeah, so
crater?
yeah, so you need to find out that in a per square kilometer, or let's say per square mile, how many craters you have, and then based on the number of craters. So while forming those planetary bodies, during that time there are many asteroids which are just because of the gravitational pull, it will just coming onto that bodies and forming those satellites or forming the planetary systems. And during formation, it actually during that region it's actually forming those craters. So by counting the number of craters in a in let's say 100 by 100 square kilometer regions from one system to another systems, we can actually find the age. That's uh, uh, that's the that's one of the process people generally use to find the age on the surface.
Okay, sir. Thank you, sir. That's all from my side.
Thank you, Prakash. We'll take the last question of today's networking event. We'll take Arun Shah sir's question. Are you there, sir?
Yeah, good evening, sir, and thank you for informative session. It was a very good session. So I'm from Nepal, and I have
Mhm.
done master in sports medicine, and I'm
Mhm.
planning to do a PhD in space medicine or
Mhm.
aerospace medicine.
Mhm.
So my question is, like we all know, like cell is the basic unit of life. So I'm more into biology, and like
Mhm.
physics, chemistry, and biology is interconnected subject.
Mhm.
So my question is in regarding like energy medicine. Like first, recently, like NASA is sending some message, like they will carry some like message in pen drive to the edge of some like to moon or in a space. So
Mhm.
what will the effect in a context of vibration or frequency to human body? And that is one question. And a tail question is like the Carl. I just want to confirm or make like the Carl Sagan when he sent like the first extraterrestrial message to the space, like to show the Earth civilization to connect
Mhm.
with different like aliens or something.
Yeah.
Uh, yeah, that's my two questions.
Yeah. So first, your to answer your first question, the vibration on the human body. So that is only for the first 5 or 6 minutes during the launching, I think. But when it will be going into the space, let's say into the, into the international space station, then you will not feel any kind of vibration. You will be just floating without any gravity, right? So when it will be traveling to the moon, there will be not much gravitational, and that's why the one main worry is the during the launching. And that's my feeling that that's why people do the training during the launching. How can they sustain during that time, during the launching time? That is the most difficult phase of the things, I think. And
So,
yeah.
like the gravitational wave travels, it takes time. So, like when we are sending some message, like right now, so it may take few months.
Yep. The message you were saying, right?
Yeah.
Yeah, that can take. Okay, so one of the important things that I was also saying, that Voyager 1 and 2, that actually sent in 1971 or 1972, I think. So on that spacecraft, there are some messages already there about the human civilization, and it already passes through the Pluto region. It is now entered into the interstellar space, and we do not know where it will be heading in later part or in near future. And we and it is now more than 50, almost 50 years since it's started its journey, and still it did not reach any of the civilized society, because from the Voyager 1 and 2 we are still getting the signal. And when, let's say, we will not be getting the signal because it is too far from Earth, then maybe at some point it will be going to another world, and we still do not know, because already we do not find any kind of life or any kind of life. So we are still not sure. We cannot say directly that who will be receiving those things. We do not have any idea so far.
Okay. Thank you, sir. Thank you for that.
So, do you have any conclusions, Arun sir? I think the questions have been answered. We have a bunch of questions that are left over. It seems a bunch of people raised their hands, a bunch of people had their questions in the chat. We apologize to you. We clearly have a time limit, but we apologize. We have given you mail, and you can mail us there. Any questions that you have, will provide you with appropriate answers. All right. We are now. I'll start with the conclusions. We are extremely grateful to Sir for giving us his valuable time. This was an absolutely insightful session. I'm a tech guy. I do tech most of the time, code most of the time. So this is not my particular niche, but I really enjoyed it. Learned a bunch about various missions. The questions and answers were really insightful. This was an absolute treat for me. Thank you so much, sir. Thank you so much for being here.
Thank you for
We'll
organizing the event.
Thank you, sir. It is always you who did the things. Thank you for just replying is back. That was even better. Now I'll start with the conclusions. I'll call upon my friend and co-founder Jitendra. He'll tell you more about propagation, what we do, and more about what you can do to propel your career further into this. He'll tell you about a winter school, the thing that we are organizing that is in much more depth. It's an 8-week program. You can do research there. You can write about research paper and a bunch more. You will get to know more about this in much more detail via him. So I'll call upon him to speak on this. You can go ahead, Jitu. Thank you for that. Mail us the questions if you have any to propagation.connect@gmail.com. We'll end the calls here. Thank you.
Thank you, sir.
Yep.
Thank you, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir.
Thank you, sir.
Thank
Bye.
you.